In question 58, we get to deal with combinatorics. I say get to because combinatorics is probably my favorite topic on this exam. It doesn't always make for good test questions, as problems tend to be more tricky than hard, but I think this problem's pretty decent. So the idea in this problem is that we have 25 identical rental trucks, and we're going to distribute them among 5 different cities. We have to give out all 25 trucks, so any city can have anywhere from 0 to 25 trucks, as long as the total number of trucks received is 25. And what I'm asked is, for which of the following subsets of the set of all possible distributions is the number of distributions equal to this expression? So kind of like Jeopardy, right? They're telling us the answer and we have to figure out the question. So what we'll end up seeing is that there's a trick to figuring out the cardinality of each of these different subsets. And the trick is this method called the stars and bars method. Stars and bars is a method for counting when you're trying to partition n indistinguishable objects to k different groups. So maybe an easier example. Suppose I have 6 cookies and there's 3 kids that I'm gonna give these cookies to. All the cookies are the same. I just need to figure out how many each of these 3 kids gets. Well, what I'm gonna do is I'm gonna draw a picture, and that picture is gonna represent one of the different ways that I could give out these cookies. Maybe we'll start out with the most fair allocation. 6 cookies, 3 kids, the most fair thing to do would be to give each kid 2 cookies, right? Here's what that picture would look like. The stars are the cookies and the bars are the partitions that allow me to distribute those 6 cookies to the 3 kids. These are the cookies that the first kid gets. These are the cookies that the second kid gets. These are the cookies that the third kid gets. What if I didn't like one of the kids? What if the first kid was kind of a jerk? But I'm not a monster, so I'm still going to give him 1 cookie. Now I got 5 cookies left for the next 2 kids. Maybe the second kid looks really hungry, so I'm going to give him 3 cookies. That leaves me with 2 cookies left for the third kid. Here's a picture representing that allocation. What's cool about stars and bars is it even allows you to consider the situations where a kid doesn't get any cookies at all. Right? Maybe the second kid's trying to lose weight, so he doesn't get any cookies at all. So I give 3 cookies to the first kid. Here's the partition. Anything left of this goes to the first kid. I'm now in my second group. I won't put any cookies down. I'll put another partition. Now I'm allocating cookies to the third kid. I give him these 3 cookies. All right, this would represent 3 cookies to the first kid, none to the second kid, 3 to the third kid. The key realization here is that these pictures are in one-to-one correspondence with the ways in which I can partition the cookies to the kid. Maybe I'll call it the options for distribution or something. So if I want to know how many different ways I can distribute 6 cookies among 3 kids, all I got to do is count the number of ways I can arrange 6 stars and 2 bars. Note the number of bars is always 1 less than the number of kids because I only need 2 bars to create these 3 different partitions. Anyways, how many different pictures could I draw? Well, you can just think it's the number of words using the letter A n times and using the letter B k minus 1 times. You got n plus k minus 1 total letters. So there's n plus k minus 1 factorial ways to permute those letters. But some of those permutations look the exact same, right? Because this star looks just like this star. So I got to divide by n factorial to account for the n indistinguishable a's or stars, and then divide by k minus 1 factorial to account for the k minus 1 bars or b's. If you've done any combinatorics, you might recognize this formula. It's just n plus k minus 1, choose n, which is equal to n plus k minus 1, choose k minus 1. That's interesting. I wonder if there's some way to see this choosing formula in this picture. Absolutely there is. Instead of thinking about putting down a whole bunch of stars and bars, think about having 8 different slots to fill. I need to pick 6 of these 8 spots to put stars in for the cookies, and the remaining 2 spots will be used up for the bars, the partitions. Or equivalently, I need to choose 2 of the 8 spots to put the bars, and the rest of them will get stars, cookies. Either thinking about the number of words with NAs and K minus 1 Bs, or choosing from the N plus K minus 1 slots where you're putting either the stars or the bars, we get a pretty easy and intuitive formula for the number of these pictures, which represents the total number of options for distributing N indistinguishable objects to K distinguishable groups. Reading through the problem, we have 25 identical, aka indistinguishable rental trucks. That tells us that n is equal to 25, and we're going to distribute them amongst 5 different cities. Cities are analogous to the kids up here. This tells us that k is equal to 5. Each city can receive any number of trucks from 0 to 25 as long as the total number of trucks received is 25. Right. We're partitioning 25 indistinguishable trucks to 5 distinguishable cities. We're told that this is the answer. We want to know which of these questions leads to this answer. Well, why don't we just solve each of these different questions? Let's start with question A. The distributions for which at least one city receives 0 trucks. I think I talked about this in a previous video. When you see this phrase at least, often it's useful to consider the complement. I think that was question 31 where that came up when we were figuring out the probability that at least two of the dice have the same number appear. And we saw that instead of calculating that directly, which involved considering these different cases, it made a lot more sense to just subtract out the number of ways that all 4 dice have different values, the complement of at least 2 of the dice having the same number. We can do something really similar here. Rather than directly calculate the number of distributions for which at least one city receives 0 trucks, we can calculate the total number of distributions and then subtract out the distributions where no cities receive 0 trucks. In other words, each city receives at least 1 truck. Okay, let's first figure out the total number of distributions without any restrictions. I got 25 trucks and 5 cities, so I need 25 stars and 4 bars. That leaves me with 29 slots. From those 29, I can think of choosing 4 of them to put my bars down in. The total number of distributions is 29, choose 4. From that, I want to subtract the distributions where no cities receive 0 trucks. In other words, each city receives at least 1 truck. How can we make sure that each city receives at least 1 truck? Well, let's just start by giving each city a truck. Then all we have to do is distribute the remaining 20 trucks. Distributing those remaining 20 trucks will be really easy using stars and bars. And because we've given each city a truck already, we know that each city is going to get at least 1 truck. So we want to get rid of the options where each city receives at least 1 truck. To count those options, we're going to give away 5 of our 25 trucks, 1 to each of the cities, and then think about how many ways can we allocate the remaining 20 trucks to the 5 cities. 20 stars, 4 bars. I got 24 choose 4 ways. Note that this is exactly the expression given to us. A must be the right answer. To get some practice, we might as well calculate the cardinality of the subsets described in B, C, D, and E as well, even though we already know the answer to the question. For B, we want the number of distributions for which each city receives at least 1 truck. Does that sound familiar? Because that's exactly what we just did here. Distributions where no cities receive 0 trucks, aka each city receives at least 1 truck. This 24 choose 4, part of my answer A, is my answer B. Is 24 choose 4 equal to 29 choose 4 minus 24 choose 4? I mean, no. If it was, this would be a terrible question. But I guess if you were taking the test and you hadn't already figured out that A was the correct answer, and you got this as your answer for B, you might want to convince yourself that this is not equal to this difference. That's not too hard to do, but it's a little bit tedious, and I'm going to have to do it for each of these different answers, so maybe I'll save that for the end of the video. For now, we'll just recognize that 24 choose 4 looks different than 29 choose 4 minus 24 choose 4, and therefore it's likely not the right answer. What about C? C talks about the distributions for which each city receives at least 4 trucks. That's almost identical to what we just figured out in B. Remember, in B, we ensured that each city got at least 1 truck by just kind of giving each city a truck right at the start. Well, if we wanted to ensure that each city got at least 4 trucks, we could just start by giving each city 4 trucks right at the start. If we gave each of the 5 cities 4 trucks, that's 20 trucks. What that means is we only have 5 left to distribute. How many ways can we distribute the remaining 5 trucks among the 5 cities? Sounds like 5 stars and 4 bars. There'd be 9 choose 4 ways to do that. Again, I don't think that 9 choose 4 is equal to 29 choose 4 minus 24 choose 4. But at the end of the video, I'll prove that fact. For now, because they look different, we'll say C is not the answer. What about D? The distributions for which 4 or 5 cities receive the same number of trucks. It's kind of a strange one. The way I thought about this is, let's first consider exactly 4 of the cities receiving the same number of trucks. I got 5 cities. I got to choose 4 of them to be the 4 cities that are getting the same number of trucks. How many trucks do those cities get? Well, there's 25 trucks total. So these 4 cities could get 0, 1, 2, 3, 4, 5, or 6 trucks. Because 6 times 4 is 24, and I only have 25 total trucks. But be a little bit careful here. You might think that that's 7 options, right? 0, 1, 2, 3, 4, 5, and 6. But one of those options won't work. We don't want to give 5 trucks to each of these 4 cities. Because if we do, then we'd have 5 trucks left for the 5th city. And we're currently counting the distributions for which exactly 4 of the 5 cities receive the same number of trucks. So these 4 cities can get 0, 1, 2, 3, 4, or 6 trucks. Sounds like 6 different options. Now I need to add in the number of ways in which all 5 cities can get the same number of trucks. Well, maybe you can just see that that's 1. I choose all 5 of the cities. I only have 1 option for how many trucks they get, 5 apiece. Looks like we got 31 ways in which 4 or 5 of the cities receive the same number of trucks. 31 is not equal to 29 choose 4 minus 24 choose 4, so D ain't the answer. Finally, E. The distributions for which 4 cities receive at least 1 truck, and the other city receives 0 trucks. All right, let's see. I have 1 city that's not getting any trucks. So I got 5 choose 1 ways to choose the city that's not getting any trucks. Then really what I'm doing is distributing my 25 trucks to 4 cities. But I have to be careful how I do so because I want to make sure that each of these 4 cities gets at least 1 truck. Remember, to make sure that each city receives a certain amount of trucks, we can just start by giving each city that amount of trucks. So we'll give a truck to each of the 4 cities. That leaves us with 21 trucks to distribute amongst 4 cities. Sounds like stars and bars. 21 stars, 3 bars. I got 24, choose 3. So 5 ways to choose the city that does not get the truck, and then 24 choose 3 ways to distribute the remaining trucks to the lucky cities. 5 times 24 choose 3 doesn't look like 29 choose 4 minus 24 choose 4, so that's not my answer either. It looks like the answer is A. As I've referenced several times, I don't love the fact that I'm relying on 29 choose 4 minus 24 choose 4 to be different than these other answers just because it looks different. So maybe we should prove that this expression is not equal to all these different counts. Rather than manipulate each of these different answers, maybe we start by manipulating this. 29 choose 4 is 29 factorial divided by 25 factorial 4 factorial. And 24 choose 4 is 24 factorial divided by 20 factorial 4 factorial. Maybe I'll call this A. If I multiply the top and bottom of this fraction by 21 times 22 times 23 times 24 times 25, I could change this 20 factorial into 25 factorial, which would give me a common denominator here. What I'm saying is that this expression is equal to 29 factorial minus the product of 21 to 25 times 24 factorial. Can I simplify that anymore? Well, at least a little bit more. I can take this 25 and the 24 factorial and call that 25 factorial. And then I can factor out that 25 factorial and a 25 factorial from here and cancel it with this 25 factorial. When all the dust settles over here, I'll have the product of the numbers from 26 to 29. Over here, I'll have the product of the numbers from 21 to 24. And on the bottom, I'll have 4 factorial. You could probably go a little bit further if you really cared to, but I suspect this will be a nice form to use when we compare our answers to these other answers. So maybe I'll stop there. So first, going back to answer B. Answer B was 24 choose 4. The question is 24 choose 4 equivalent to this mess? Well, 24 choose 4 is just 24 times 23 times 22 times 21 divided by 4 factorial, right? The 20 factorial that's in the denominator, canceling with the product of the whole numbers from 1 to 20. And if we look at this and compare that to answer A up here, conveniently we have the same denominator, so we just need to compare the numerators. Note that what's written over here and what's written here is identical. So all we need to show is that this thing is not equal to twice this thing. And I think I can call that obvious, right? Maybe we can make a prime factorization argument. This number has a 29 in its prime factorization. This number does not. These two things are not the same. What about showing that C does not equal A? Well, C is just 9 choose 4. Maybe I can cheat and write this here. 9 choose 4 is 9 factorial over 5 factorial times 4 factorial. But I can cancel the 5 factorial in the bottom with part of the 9 factorial up top. And I get 9 times 8 times 7 times 6. Again, all I have to do is compare the numerators. I think it's fairly obvious that this minus this is not the same as this, but sure, I'll write it out. If I added this term over to the other side, let's see, this 9 is 3 times 3. So I could think of 9 times 8 times 7 times 6 as 8 times 21 times 18. Kind of taking one of the 3's and multiplying it with the 7 and the other 3 multiplying it with the 6. And then note that 8 times 21 times 18 is less than 22 times 23 times 24. So this expression right here is less than 22 of these 22 times 23 times 24 things, right? 21 of them from over here and 1 of them from over here. And this is certainly less than this. Therefore, this expression is less than this expression. Probably a smarter way to do it, but that gets the job done. D is really easy. D is 31. D is less than C. We've already shown that C is less than A. Therefore, D does not equal A. Finally, quantity E. I got 5 times 24 choose 3. 24 choose 3 is 24 factorial divided by 21 factorial 3 factorial. I can cancel this 21 factorial with most of this 24 factorial. That leaves me with 5 times 24 times 23 times 22 up top. Down on the bottom, I got 3 factorial. But I don't want a 3 factorial, I want a 4 factorial because that's what I've had in all my other answers. So I'll multiply the top and the bottom by 4. That gives me 5 times 4 is 20. So 24 times 23 times 22 times 20 divided by 4 factorial. I just have to show that this quantity is not the same as this quantity in blue, Multiplying both sides by 4 factorial, I'll just have to show that the product of the numbers from 26 to 29 minus the product of the numbers from 21 to 24 does not equal 24 times 23 times 22 times 20. Maybe I'll again add this term to this side. Then I can factor out 22 times 23 times 24. What I'd have left is a 20 over here and a 21 over here, so 41 total. But these two quantities can't possibly be the same because this quantity has a 29 in its prime factorization and this quantity clearly does not. E is not the same as A. This question wasn't a bad question. Only one of these 5 quantities is equal to 29 choose 4 minus 24 choose 4. You certainly wouldn't want to take the time to do this kind of proof on the exam, but it never hurts to get a little bit more practice with factorials.